All right. I apologize for taking so long to get something more to you all. It's been a long week, and I've actually tried this many times now without getting it to work. So let's see if I can get it to work this time. I want to walk through the chapters on logic in the textbook. That's specifically Appendix A1 and A2. Now, I'm assuming that you already know a lot of this. I'm hoping you do. And if you do, then this is basically a review. If you don't, the text is pretty clear. You should be able to read it fairly carefully. Let me just walk through and highlight the main ideas from those sections. All right, so first of all, Boolean logic is called Boolean algebra, and or it's related to something called Boolean algebra, which is using variables and mathematical operators to describe logical statements and so on. So here's the first way to think about it. When you think about normal algebra, you have something like x plus y times z. Think about that as being a bunch of variables, x, y, and z, that stand for numbers. And that means those numbers can take on a range of possible numeric values, usually real numbers. And then there's operators, plus and times, on those numbers. So Boolean algebra is the same thing. You have something like what I have written there, which is P or Q implies R. Variables, again, P, Q, and R, that stand for statements in this case. Statements can take on only the values true and false. So P is either true or false, Q is either true or false, R is either true or false. And then those operators, or and implies, or that is if then, are operators on those Boolean values. Now, let me say something quickly. It's difficult to get the or and the and so on to show up in Word. So what I've got right now is sort of the best version I could get for now. That or is a little too curvy for my taste, but you can see a slightly better version in the book. All right. The point is that statements are either true or false, never both. Always at least one of them. We don't have to know whether they're true or false, but that's one of the values they have. So you can see the book for more on that. You've used Boolean variables, of course, in programming, and they follow exactly this algebra. So the important thing is they have two possible values, true or false. Now the operators involved, there's 5 of them, and I'm calling them operators. The book calls them connectives, but technically negation is not a connective, because it doesn't connect any two things. It just is in front of one. But they're at least all operators. And they're listed here. They're negation, conjunction, disjunction, conditional, and biconditional. That is not, and, or, if then, and if and only if. And you can see the symbols right over there. And you should know the symbols well. This should be something you just have memorized. And the exact behavior of each operator is given by a truth table. So that first truth table here for negation tells you how negation works. The first column is for P, the second column is for not P. This tells you that if P is true, not P will be false, but if P is false, not P will be true. So that's a way of saying that the value of not P is the opposite of whatever the value of P was. Conjunction, or and, follows this truth table. This tells you that if P and Q are both true, that P and Q will be true. And if one of P and Q is false, or both are false, then P and Q will be false. So these are basically, you can work these out for each of the different operators, and it basically defines how that operator works. I won't say much because you're used to these from programming anyway. Disjunction, here's the truth table for it. P implies Q. Here's the truth table for it. Implies is worth noticing because it's easy. People sometimes get it wrong. True implies true gives me true. True implies false gives me false. False implies true gives me true, and false implies false gives me true. That should make sense. The idea is that think of P implies Q as some sort of a sentence which makes a promise. Like if I say to you, if you get a C, then you'll pass the class. If I say, if you get a C, then you pass the class, P is you'll get a C, and Q is you'll pass the class. But if I actually promised you that you will get a C if I say that? No, I've just said that if you get a C, there's something that'll happen. I've actually promised that you will pass the class. No, that's why, and I've just said that you will if you get a C. So notice that I can have either one of P or Q being false, and I might still get true for the whole statement. So then think about the statement. What's the one case, what is the, when would you consider me to be lying? If I say, if you get a C, you'll pass the class, and then you get a C and you pass the class, that's the first row, then of course you consider me to have spoken the truth. On the other hand, if you get a C and don't pass the class, then you'll consider me to have been lying. The if then had to be false. But if I tell you, let's go to the last line, if you get a C and if I say, if you get a C, you'll pass the class, and then you don't get a C and you don't pass the class, of course you would consider me to have spoken the truth. I never said you would get a C. I just said that if you did, that something would happen. And I didn't say anything about what would happen if you didn't. And the last line, the third line, is also really important to notice. If I say if you get a C and you'll pass the class, and then you don't get a C, but you pass the class anyway, I wasn't lying, because I didn't say anything about what would happen if you didn't get one. So that was still a true statement on my part. Biconditional is an if and only if. It means P implies Q, but also Q implies P. And one way to think about it is it means that P and Q are equivalent to each other. They're either both true or they're both false. So an example would be, if today is Friday, then tomorrow is Saturday. If P is true, today is Friday, then Q will also be true. Tomorrow will be Saturday. But on the other hand, if P is false, today's not Friday, then Q will also be false. Tomorrow won't be Saturday. So they'll either both be true together, or they'll both be false together. That's because P and Q, P is true if and only if Q. Today is Friday if and only if tomorrow is Saturday. It's used for equivalent statements. And if P and Q are different, then you get false. So you can think of this meaning P and Q have the same value. True if they're both true, true if they're both false, false if they're one of each. Then the book has a section about conditionals. P implies Q is known as a conditional. It's like if P then Q. I've given an actual example on the right. If that's a cat, then it is a mammal. The book calls P the premise and Q the conclusion. That's not the best terminology. Premise and conclusion is better reserved for whole arguments, which involve more than one statement. I would rather call them the other common terminology, which is antecedent and consequence. So the first one, P, is the antecedent. The second one, Q, is the consequence. So if that is a cat, then it is a mammal. That is a cat is the antecedent. It is a mammal is the consequence. Okay, what else? There's 4 important related statements. If you have the conditional P implies Q, you can also consider what happens if you reverse P and Q, and that gives you the converse. Q implies P. You just get it by reversing the statements. Or you can keep the statements in the same order, but negate them. Not P implies not Q. Or you can do both together. Not Q implies not P, and that gives you the contrapositive. So the idea is that the conditional statement we start with, if that is a cat, then it's a mammal. Reversing it, we'll say, well, if it's a mammal, then it's a cat. And the inverse will say, if it's not a cat, then it's not a mammal. And the contrapositive will do both a negation and a conversion, and we'll say, if it's not a mammal, then it's not a cat. Now, the important thing to notice is just because the conditional is true doesn't mean the converse is. Just because if it's a mammal, if it's a cat, then it's a mammal, doesn't mean that it's true that it's a mammal, it's a cat. Matter of fact, that's probably not true. So the conditional and the converse are not the same as each other, and the conditional and the inverse are not the same as each other. But the conditional and the contrapositive are exactly equivalent. If the conditional is true, the contrapositive is true. If the conditional is false, the contrapositive is false. So if that's a cat, then it's a mammal, is equivalent to if that's not a mammal, then it's not a cat. You get to the contrapositive by reversing and negating. By the way, the converse and the inverse are also equivalent to each other because the contrapositive of the converse is the inverse. If you start with the converse and first negate it, you get this, and then you get the converse of it, you end up with this. So the converse and the inverse are contrapositives of each other. So these two diagonally are the same, and these two diagonally are the same, but they're not all 4 the same. One of the most important skills you need to know for this chapter is how to build a truth table for a Boolean expression. So let me show you how to do it here. I've got it mostly completed. I'll do the rest on sort of online right here as I talk. So you start with a longish Boolean expression, longer than just P or Q or P implies Q. Something like this. That says P and not Q implies not P or Q. Okay. And you start by looking through everything that's in the list, the entire expression, and finding out every variable you've got. So you've got a P and a Q. So I create a column for P and a column for Q, and I set up my 4 rows for those. I said these are my 2 guide columns, and I write down every possible way that those two things can be true and false. Either they can both be true, or the first one can be true and the second one false, or the first one false and the second one true, or both false. You should probably memorize this pattern of trues and falses right here. It's the same pattern we used up above for all of our other truth tables, so it should be familiar to you. You can see it up here over and over and over. Here's that pattern. True, 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 false, false, true, false, false. True, down here, true, 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 false, false, true, false, false, and so on. Okay. Then what you do is you work your way forward in this, trying to work one operator at a time. Your goal is to and think about how you'd actually evaluate this. In other words, the first thing you have, the very last thing you can evaluate is this implies. Because to evaluate the implies, you have to know everything on the left side and everything on the right side. So the very last column I do is the implies. Before that, I have to do smaller things. So the first thing I'm going to start with is the not Q, because I can do that just on its own. And then I can do the P and not Q. So that's this next column. And then I can do the not P because I can do it on its own. And then I can do the not P or Q because that's over here. And then finally I'm able to do the whole piece. You can do these in a slightly different order, but you always have to be, there's certain orders won't work. So let me show you how you do this. I take the first thing, not Q, I write down a column for it, and then I figure out if P and Q have these values, what value does not Q have? The key here is that Q already has a column. It's right here to the left. So since I know what Q is, I know what not Q is. Because not reverses everything, negates everything. So if Q is true, not Q must be false. And if Q is false, not Q must be true. And so on, this must be false and this must be true. And now when I come to this one, I'm focusing on the OR. This is the OR column. I mean the AND column. So this AND is connecting P and not Q. And I already have a column for P, and I already have a column for not Q. So I'm looking at whatever P is here, true, whatever not Q is here, false, and then putting them together with an AND. So true and false gives me false. True and true gives me true. False and false gives me false. False and true gives me false. And I'm ready to do not P. Well, P is true over here, so it's false over here. It's true over there, so it's false over here. It's false over there, so it's true over here, false over there, so it's true over here. Now we have not P or Q. So here's not P, here's Q. That means I'm doing this or that. So I have false or true, which is true. Then I have false or false, which is false. Then true or true, which is true. And then true or false, which is true. Then finally I have this thing implies that thing. So this thing is this column here. And this thing is this column here. So I'm doing this implies, hold on, this implies that. So I've got false implies true. False implies true, if you look it up in our other truth table, is always true. True implies false, on the other hand, is always false. False implies true is true. And false implies true is true. Okay, and that's my answer. So you need to know how to do that. By the way, if you do this and you get a column that's all T's, all trues, that stands for something as a tautology. If it's that's called a tautology. A tautology is something which always is true no matter what the individual values of P and Q are. So if something's a tautology, it means it doesn't even matter what you're talking about, what the statements are about. By the very form of it, it always has to be true. The simplest tautology is if I just say P or not P. Because anything I say about no matter what P is, that will be true. For example, if I say today's Friday or it's not Friday, I'm really sure that I've spoken the truth about no matter which one, no matter what day it is. Okay, if it's all falses, then it's called a contradiction. If two columns are the same, then they're equivalent. So this column right here, true, false, true, true, is the same as this one, which means that this longer expression is actually completely equivalent to this last expression right there. So what that means is if you were dealing with this in some sort of Boolean algebra context, you could actually replace the whole expression by just this much smaller one right here. And if you were to do another truth table, you could discover that that in turn is actually equivalent to just P implies Q. Because if you look at P implies Q, it has exactly the same column. So you have all these different things that are equivalent to each other, and that's sometimes helpful to know. Okay. Here's another example that has 3 different variables. I just want to show you how to do one with 3 variables. P implies R is equivalent to, or if and only if, Q and R. So here I have 3 different variables, P, Q, and R. So I have 3 guide columns labeled P, Q, and R. And so I need 8 rows for all the different possible ways these things can be set up. First of all, they can all be true. Second, the first 2 could be true and R could be false, and so on. So you should also memorize or just learn the pattern for this in case there are 3 variables. I won't give you anything with 4, but you should be able to do that too. The pattern here is that R alternates true, false, true, false, true, false, true, false. Q alternates 2 trues, 2 falses, 2 trues, 2 falses. And P alternates 4 trues and 4 falses. Another way to think about that is the the first 4 rows are exactly the same as our normal 4-row pattern. And that's repeated twice, once with a bunch of trues in front of it, and once with a bunch of falses in front of it. In any case, now we do the same things before. I start with P implies R. I already have a P column and I already have an R column, so I can do that here. True implies true, gives me true. True implies false, gives me false. True implies true, gives me true. True implies false, gives me false. False implies true, gives me true. False implies false, gives me true. False implies true, gives me true. And false implies false, gives me true. Here I've got Q and R. That's these 2 columns. True and true is true. True and false is false. False and true is false. False and false is false. True and true is true. And then 3 more falses, just like before. And then finally we have this column implies that column. So, no, is equivalent to that column, if and only if that column. It's also called is equivalent to. So T if and only if T is true. False if and only if false is true. But here they're different, so it's false. Here they're the same, so it's true. Here they're the same, it's true. And the last 3, they're different, so it's false. So this is the answer to finding the truth table for that particular expression. All right. Let's talk finally about the properties of logical operators. I want you to notice, first of all, that AND is commutative. Now think about what commutative means with numbers. If I say that addition is commutative, I mean that you can take, for example, 3 plus 4 and it's going to be equal to 4 plus 3. Doesn't matter which order you put the numbers in, when you add them you get the same result. Well, AND is commutative too. So P and Q is equivalent to Q and P. Doesn't matter which order you put them in, you get the same result. OR is also commutative. Implies if and only if is not commutative. Then AND is also associative. Think about the difference between commutative and associative with numbers. With a number, 3, 4, and 5, when you say that it's associative, you mean that if you have 3 numbers and you add them twice, it doesn't matter whether you parenthesize the first addition and do that addition first and then do the second addition, or whether you do the second addition first and then do the first addition. You get the same result. So up here, I've got 1 addition and 2 operands, and I switch the operands, the numbers. Down here, my numbers don't change in order at all. It's always 3, then 4, then 5. What changes is which of these 2 pluses gets done first. Oops. Which of these 2 pluses gets done first? So that's associativity. Well, AND is associative as well. So P and Q and R is equivalent to P and Q and R. And OR is also associative. Once again, if and only if, if then is not associative. By the way, if and only if is associative commutative also, but most people don't bother to worry about it because we don't use that very much. And distributes over OR. So let's think about distribution with numbers. We say that times distributes over plus, a multiplication over addition, because if you have a multiplication on the outside and then something in parentheses with plus on the inside, you can distribute the 3 times inside and take it times the 4 and also times the 5 and leave the plus on the outside. Notice that what we've done is the 3 times is moved inside, so we get 3 times 4 and 3 times 5. And the plus, which used to be inside the parentheses, is now the one thing outside the parentheses. Okay. That's distributivity. And it turns out that AND is also distributive over OR. So you can distribute the AND over OR in the same way. By the way, the opposite of distribution is factoring. This says I can look at the thing on the right and factor out the 3 times out in front. So another way of saying distribution works is to say I can factor. Weirdly, OR also distributes over AND. I put an exclamation there because that's not the way numbers work. You can't distribute addition over multiplication at all, but you can distribute OR over AND as well as AND over OR. One of the things we've talked about before that you should be aware of is the question of whether not distributes over OR or AND. So if I have not P and Q, is that equivalent to not P and not Q? And the answer is it's not. But it turns out to be equivalent to not P or not Q. So if you have not P and Q, you can distribute the not as long as you switch the OR to AND to an OR. You've seen this before in programming. And if you have not P or Q, you can distribute that as long as you switch it to not P and not Q. That's called De Morgan's law. Again, you can think about it backwards as factoring the not out as long as you switch the OR to an AND or vice versa. All right. On page 586, they have a list of common properties of logical operators, and you can see all these things we just went through, plus one of the thing on the contrapositive that we talked about before. And you'll be using that for some of the assignments. I apologize for taking so long to get this out. I will try to do a video in the next couple days on the first part of chapter 10, which deals with logic as it applies to combinatorial circuits. I'll also try to do a quick video on A3 on proofs, and I'll show you maybe one that shows you how all the stuff works together. For now, you should be looking at logic 1, at homework 1 and test 1. There's a study guide for test 1, and there's an assignment sheet for homework 1. Neither of them are due until a week after I get back. So anything I don't get to in the next week, I won't worry too much about it. I'll make sure that you have enough time to do it. We'll just maybe start a little late and when we get going. So don't sweat it if this is the only thing I get to you. If I can get some more stuff, I will. But take a look at this. Make sure it's really comfortable for you, that you're able to do most of it. And if I get you more videos, terrific. If I don't worry about it. The first day I'll get back, I'll sort of catch up with you all and make sure that all this makes sense. You won't have anything actually due until then. I also do owe you a response on the candy problem. So I think I do. So I'll get back to that as well. Okay. Thanks.